Decision point procedure. The purpose of the decision point procedure is to reduce the minimum required fuel and therefore be able to increase the traffic load. When using the decision point procedure, the contingency fuel is reduced by calculating contingency fuel only from the burn-off between decision point and destination. The trip fuel to the destination aerodrome is calculated via the decision point. Delaying arrival. We use a U-shaped approach for teaching this. The questions will either come in the form of an indicated airspeed or a Mach number. For an indicated airspeed, use the CRP5 and temperature and altitude to get a true airspeed. If you're given a Mach number, use the formula TAS over local speed of sound. You'll need the temperature to do this. Once you've got the TAS, add or subtract the wind, depending if it's a tailwind or a headwind, to get the ground speed. Using a speed distance time relationship, calculate the time required to cover the distance at the ground speed that you've just calculated. In minutes, add the delay which is given in the question, for example 5 minutes longer, delaying the arrival, and you'll have a new time. Divide your original distance by this new time and you'll get a new ground speed. Now just go back up the other arm of the U, so to speak, with the new ground speed. If you added the wind before, subtract it now. If you subtracted the wind before, add it now. That will get you a new TAS. If you've left your CRP5 alone from before, you can now just read across the new indicated airspeed. And if you kept your local speed of sound from before, you'll be able to calculate your new Mach number. For example, an aircraft at flight level 120, indicated airspeed 200 knots, outside air temperature -5, and a wind component of +30, is required to reduce speed in order to cross the reporting point 5 minutes later than planned. Assuming flight conditions do not change, when 100 nautical miles from the reporting point, indicated airspeed should be reduced to. So using the CRP5, line up -5 degrees Celsius with 12,000 feet in the airspeed window. Then using the inner scale, look for 200 knots, and on the outer scale read a TAS of approximately 242 knots. To this add the 30 knot wind component, resulting in a ground speed of 272 knots. Using the speed distance time relationship, divide 100 nautical miles by 272 knots to get a time of 22 minutes. To this add the 5-minute delay to get 27 minutes. Now divide this 27 minutes into the fixed 100 nautical miles to get a ground speed of 222 knots. Subtract the wind component from this to get a TAS of 192 knots. Now if you've not changed the position of your CRP5, just read from the outer scale 192 knots TAS to the inner scale of approximately 158 or 159 knots indicated. Here's an example on delaying arrival with Mach number. An aircraft at flight level 310, Mach 0.83, temperature -30, is required to reduce speed in order to cross the reporting point 5 minutes later than planned. Assuming that a zero wind component remains unchanged, when 360 nautical miles from the reporting point, Mach number should be reduced to. Using the formula Mach number equals TAS over local speed of sound, first of all calculate the local speed of sound from the temperature minus 30 degrees Celsius. Add 273 to get 243 and take the square root of this to get 15.59. Multiply this by 38.94 to get a local speed of sound of approximately 607 knots. If this is multiplied by the Mach number of 0.83, the TAS is 504 knots. Since there's a zero wind component, the ground speed will also be 504 knots. Divide the distance of 360 nautical miles by 504 knot ground speed to get 43 minutes. To this add the 5-minute delay to get 48 minutes. Divide the distance, which has not changed, 360 nautical miles, by 48 minutes to get a new ground speed of 450 knots. This will also be a TAS of 450 knots since there was a zero wind component. Using the local speed of sound from earlier of 607 knots, calculate a Mach number of approximately 0.74.